Okay. Thank you again for being here. Today I'm going to talk about listening to data, visual learning from multi-level. First, thanks to Wolf introduction, I just finished my PhD with Professor RU at Johns Hopkins, and I'm coming postdoc at Berkeley. So about me, previously I was, before I'm a full-time nurse doing PhD, I was an amateur dancer, and also I used to play with supercomputer, robots, and also I have two cats who look like dogs. This one looks like dogs, this one behaves like dogs. No, okay. Now, since we are using Twitter to learn research, do research, and talk about research, so let's see what's trending now. So obviously, it's a large language model, right? Some people think, to protect myself, I do some mask language modeling on some certain names so that won't get me into trouble. Some people think, ChatGPT is scarily good, so dangerously strong AI. Some people think, it's not even dog level or cat level AI, and some people's idea would vary, whether this large language model is from a certain company or not. So it's a very controversial topic. And also some certain companies' stock has been influenced a lot. Okay, so as large language model has basically taken the world by storm, especially for me, during CVPR's supplementary material, I remember I was supposed to talk about research with my advisors, but instead we talk about all this open and gossip every day instead of talking about research. So it's definitely taken a lot of my time. But as we know that many smart animals, like what I'm showing here, don't really have language to show some certain levels of intelligence. This is my cat, and that is my face that my cat is sitting on to get my attention. So definitely really, really smart without needing any language. So in here, we want to ask a more scientific question. How far can we go from pixels alone? So ever since here, everything I'm going to talk about, except for the language I'm using right now, doesn't really contain any text. It's just pure visual data. So here I'm going to present a paper called Sequential Modeling Enables Scalable Learning for Large Visual Models. This is a joint work with Jan, Kartik, Amir, Alan, Trevor, Jitendra, and Milusha. Okay, so as a self-supervised learning person, I started my PhD by doing pretext tasks, and then it's contrastive learning. And then when it comes to transformer area, there's some work that kind of bring back the in painting mask on encoder thing. For example, this one is local. They don't really show good scaling behaviors yet. So for example, by scaling behavior, what I mean here is if you throw in more data and also you throw in you make the model larger, would your model perform better at all the kind of downstreams? For example, in mobile time, people try to add Instagram data into the training, but that doesn't seem to improve either ImageNet result or Coco result, any downstream result. And also, so when it comes to transformer area, I thought, okay, now since transformer is more parallelized and is good at scaling up, I was very excited. I thought maybe I can try to scale MAE to see how that goes. And then I was very depressed for a bit because in this figure, what did I do? I tried this x-axis meaning like different number of pre-training data. The y-axis meaning after you pre-train the model and then you get a representation, you fine-tune the model with top one accuracy. I mean, this is basically the standard paradigm of the previous representation learning that you pre-train a model with some certain amount of data, and then you throw out the MLP, the decoder, only leave this encoder, and then you fully fine-tune the model. So this is ImageNet 1K result. Not bad, right? But the problem is if I try to add in more data, like if I add in ImageNet 21K, the full ImageNet 1K result, basically like 10 times larger than the original ImageNet 1K. I don't seem to get higher ImageNet top one accuracy. In fact, I got a little bit worse. And what's even worse is like if I carefully fine tune, if I carefully pick the layer-wise learning rate decay factor, somewhere between 0.65 to 0.75 during fine tuning stage, I can get a pretty decent ImageNet fully fine tuning result with only a quarter of the data. It's just 0.3 difference on the scale of 85 something. So that means, adding more data doesn't really help with this kind of whole paradigm of pre-training or representation learning. So in this paper, so the previous representation, let's revisit the previous representation learning paradigm. What we do, we pre-train on ImageNet, usually, sometimes COCO as well, and then we keep our pre-trained weight, and we hope we can generalize to other data sets, and then we add some head, either detection head or segmentation head, or some MLC layer for classification, and then we fine tune the model, hopefully, and we hope it generalizes. So here, we want to get rid of all this previous paradigm and redo the whole thing from the beginning. So first, I'm gonna explain what we do directly, and later I'm gonna explain why we do that. So instead of training on ImageNet and hope it can generalize to other data, MAE trained on ImageNet for 1,600 epochs. Instead of doing that, we want to see, what we want to do is, how about instead of spending our compute or overfitting ImageNet, can we do something else? Can we just train every kind of data that we can find, but instead of 1,600 epochs, we train it on one epoch? So here we collect 1.68 billion of images, and it's across 50 data sets. And instead of using mask autoencoder with autoregression loss, we choose to use autoregressive model with cross-entropy for next token prediction. So here, so this is basically long story short. Intrinsically, we find out this is a debate between BERT versus autoregressive model. So usually, we actually find out that autoregressive model scaling behavior is better than BERT, probably because BERT is only trying to model part of the sequence or sentence, while autoregressive model is trying to model the whole sequence. So every token autoregressive model needs to predict it. So it's kind of like more general mask. So here, after there would be some more results, if you're interested, I'll show you later, to show that autoregressive model can actually have a better scaling behavior. And that is
sorry, just a question. So when you say autoregressive next token, is the token a patch or is it token the whole image?
The after tokenized like for one image is for one 256 by 256 image, we use a V2 GAN to tokenize it, and it's going to be 16 by 16 tokens.
So you do one at a time.
Yeah.
And then next image.
Yes.
Or this is just pure image, no video.
We are gonna get there.
Okay.
Okay. So yes, instead of first pre-train on some task, on some loss, like in MAE, first pre-train on L2 loss, and then you fine tune it maybe on totally orthogonal loss like classification loss. Here we just simply do prompting. You can also fine tune it with next token prediction, but at least this is consistent among pre-training and post-training. But here, what we do is we just simply prompt the model. Yes, and then let's get to the most important question.
Could you say something more about prompting? How do you prompt it?
Yes, you give some. You're gonna get here too. I'm gonna show you some examples about how do you prompt it. Language is cheap, and I need to see the pixels.
Okay.
Yes, so then one of the most important question is, across 50 dataset, how can we make use of all 50 dataset? Because you don't really need to watch into the details about this image, about this table, but all this data we collected, download from internet, it contains images, videos, supervised data, unsupervised data, synthetic data, real data, all kinds of tasks like detection, segmentation, key point detection, low light, highlight, and also 2D, 3D, 4D. I don't know how to revamp it, maybe 4.5D, whatever, this kind of data. So how can we make use of all of them altogether? So inspired by the language, the term of language sentence, we come up with something like visual sentence. For example, for one image, this is for one single image, this is also my cat. We would use a VQ-GAN tokenizer to tokenize one image into a bunch of tokens. You can imagine this just being a sentence. And if we have a video that is basically image with temporal transformations, you can build it instead of a sentence, but this time it's like a parable. A longer sentences, but with something that, is some connections among all this bunch of tokens. So yes, during training, you still do the next to completely the same. And also, if you have, this is rendered 3D rendered data from Observerse, which is like synthetic 3D data set thing. You can build it as images, but with this time, instead of temporal transformation, you have post transformation. So also you can build them as a paragraph or longer sequence and treat them as one kind of sequence. Or this is one of my favorite characters, Mr. Bean. Or if you have some, this time identity transformations. For example, one PhD student, another PhD student, another PhD student, another PhD student. This is also different identity, also contains some inherent connections among them. So you can build them as one kind of a transformation or one kind of image sequence as well. This is also be considered as a visual sentence. Or something that is more complicated. If you have some data that is annotation, in this case, then this visual sentence would be something like, give me all the skeletons of the human body, because this can also be viewed as some transformation. Imagine this is a video, and imagine if I'm in a cartoon and I was being shocked by some whatever this random stuff, and my skeleton showed up, something like this. Or you have style transfer, and you have detection. You have low light, highlight, and constant. This you can all view them as some kind of transformation as well. Or if you have free form annotations, for example, sometimes I want first detect the object and then select it. Or I just want some combinations of depth estimation, surface normal, edge detection. Or sometimes I want some data from Kitty that you have like 2 cameras. Will work too, as long as you organize them into a consistent transformation in one visual sentence. Because every visual sentence in my mindset demonstrates some kind of transformation. And if you have videos, sure, that's simple. And if you have videos with allocation, you can also formulate them as some kind of transformation too. So in this way, by proposing visual sentence, actually we can basically organize all different kinds of data as into a visual sentence and simply tokenize them and do next token prediction to do the pre-training so that we can make use of this all kinds of different data. And then if we look at the distribution of this data set, this data set, the majority of them is coming from Lion. So ideally, I have enough money that like, I can pre-train the whole thing like 4K times. I would do that, but we don't have that much money. So I basically train this whole thing one time. Then why do I decide the science thing should contain the majority part of it? So in my mindset, if we compare this to GPT-3, when they have common crawl that contains 410 billion tokens, and the rest of the data sets like Wikipedia or WebPass2 that is more high quality, but somehow like less data. Then the common crawl, which is also web data set that basically contains a little bit of everything, should contain the majority part of it to ensure the diversity of the whole data set. So here, in my mindset, the Lion thing is also a web data set that is very, very diverse. So here I also set this up as like the majority part of it. And what is the balance between this annotated data and unannotated data? As I said, what is the main purpose of this model initially from the very beginning? It's scaling behavior. What does scaling behavior mean? So in my mindset, scaling behavior meaning like the prediction is so hard that your model have to learn, you can't cheat. For example, if I only have some kinetics videos, that everything's background is the same and everything's gradually changing, then my model, what we observe that my model don't really have to predict anything to be able to get at least 80% of the things right. For example, if the background never changed and I'm moving very slowly, then the model can just guess, 80% every time 80% of the things doesn't change. I want to break this all the possible shortcut the model can learn. How do I do that? We just make sure that the transformation of the visual sentence is so diverse that model has to learn. So I got this question a lot that people ask me, do you think if it's just video, also without text, can this work? Based on my experiment, I think if it's just with the current video data set, from our experience, it won't, because the current video data set is very biased, and not very diverse. It's just mainly human activities and is very short and doesn't move that much. But video in general should work. For example, if consider now I'm not giving a talk, but I'm in a bar and the lighting is shining right here. I don't need to manually construct this low light, highlight pair to be able to feed that information into the data. But now, since we don't have that diversity yet, so we have to manually create this kind of diversity to ensure that the prediction is so hard that the model needs to first look at the context and to be able to predict, so that there will be less chance for the model to cheat. So this is the whole mindset. And also from other point of view, why do we have this kind of image with annotation data? So I was told by Jitendra that since the beginning of computer vision, every task is so hard that it's really hard for people to make progress. So they actually disentangled computer vision problem into some tasks. Sometimes you do recognition, sometimes you do detection, sometimes you do segmentation, you do 2D to 3D, you do low level, you do high level. You basically disentangle the real world complicated problem into this kind of very ideal, only one dimension task. But what happens if we want something that is like ChatGPT? Can you generate me a joke that is about, Jianbo, and it has to be about computer vision and it has to be funny? It can actually do that based on the fact that it knows a little bit of Wikipedia to know about Jianbo. It knows a little bit of a joke. And after seeing a little bit of everything data, it has some, with a large model, it has some interpolation ability at least. I cannot say that there's true generalization ability there, because if there's never Wikipedia, I don't think it would know the Jianbo, right? But as long as it has a little bit of this kind of data, then the model at least can start to do something that is a little bit more complicated. But imagine in real life, when we're driving, it's rainy, it's very dark, and there's a woman that walked past our window, and she's walking while rotating, and very dark outside. It's not a simple object detection problem. It's not a simple low light, highlight enhancement problem. It's not a simple derailing problem. It's everything together. But so that is also revealing the motivation of adding all kinds of data in the visual sentence. That is, I want at least the model to have some ability that can try to model this real life complexity. Since we know that the true generalization may not exist, then how about we train it with every kind of data we can find?
Quick question.
Yes.
So I noticed that you had, at least schematically, you had beginning of sentence and end of sentence tokens.
Yes.
Did you have any other tokens that are not purely visual data? For example, let's say you're taking the 3D data with rotations of objects, etc.
No.
Was there no pose annotation or anything that you needed to provide? Okay.
Not yet. No, because the beginning of sentence, end of sentence thing is just to because we have a lot of single images, and we want to save some, because then we can actually do packing to save some money, basically.
Yeah, I was also going to wonder.
Yeah.
How long were your full sentences?
Yeah.
Each
So
image is presumably costing you 256 tokens. Is that right?
Yeah, each image is 256 tokens, and again, constrained by our computation is 16 frames now. But yeah, but this can be extended later. And then this is training loss. So as we mentioned before, instead of training on 1,600 apples, what we're doing here is we just train one apple with every kind of data. So then except for the fact that it's really obvious that, larger model obviously have a lower loss, except for the fact that it's have lower loss. What interests me as well is something like, it keeps decreasing. What does it mean? The data, every data the model sees is a totally new data. If it doesn't learn something that can generalize, or it doesn't have the knowledge that can share with the new data, the model cannot just keep decreasing. So that means by formulate all this kind of data into the similar format, the visual sentence, at least some knowledge now can be shared so that the model can keep decreasing. And also, this two figures also really fun too. So, let me first explain what is perplexity. Perplexity is kind of like cross-entropy. For example, if I have something to predict and I have a ground truth, if my prediction is very similar to my ground truth, then I get a lower perplexity. So basically here means if you have lower perplexity, that means your prediction is closer to the ground truth. So then with different model sizes, we tested it on from low-level tasks to high-level tasks, like edge detection, low-level tasks, surface normal estimation, depth estimation, all the way to semantic segmentation. With Yutong is you can see that with larger model size, we have lower complexity. That was not surprising to me because it's just the loss. Also, we observed that larger the model size is, you have better complexity. But it's actually across all different kind of tasks, low level, high level. It's not something that just happens with one task. And also this figure is quite interesting too. Let me explain a bit. So the orange bar here is same model, but you only trained with annotated data, like every task related data. You just trained on this. Ideally, if you overfit just on this, you should have better perplexity on all these four tasks, right? But we find out that if you add more video in, you get the green bar, which is actually lower complexity across all these tasks. What does it mean? It means that some video data can actually help with some image tasks, sometimes it's low-level tasks, sometimes it's high-level tasks. Why? Because because of this formulation, if you have a better understanding of what is sequence or what is this kind of transformation, it can actually help with some image tasks as well, which is also formulated as some kind of transformation in this context. So I really like this. And then if you add more images, it give you even more complexity on this task. Okay, now let's see how it's from. This is like visual. Let's start with something that is most straightforward, sequential problem. Basically, I give an image I give the model a bunch of images, tokenize them, and then I predict the next 256 tokens. Basically, just let it generate one image. And then this is the person that gradually walking past the camera. And this is the model generated. The man's gone, or the woman's gone. Then we have some more examples. This is a woman walking in the kitchen. And you can see that there will be a door here, and there's a lighting here. So with the camera view change, you will have a door with some reflection lighting. Oh, I like the second one. This means, oops, this is, so you need to turn your head like this, and this is when someone's phone drop off, I think. So it's kind of off. Yeah. Right. We have some more examples. If you want to generate more frames, and if you need longer context, we use 16 for training, but you can do sliding window in this case. But one thing I need to mention here about the sliding window is since visual data is not like language data, it means like it's not perfectly reconstruction. You have some loss. So that when one of my advisors asked me if we can generate me an hour of video, that is probably not possible here because the quality would decrease because it's first of all, it's not trained with that long of attention. And second of all, it's because since we don't have this kind of perfect reconstruction, sometimes the reconstruction loss can propagate. But still, if you just want to generate like 4 more frames, I don't see that being a big problem. And we show some more results, and there will be a ton like pages and pages of result in the appendix in the paper. You can check it out. Okay, then let's try something. This is also sequential prompting, but this time we train this object verse repeating, right? So then we prompt the model with something like this. It's not surprising because the model thinks something similar than this. So the model just keep rotating. This is something that the model has never trained before. So the model see a little bit of ImageNet category-based visual sentence. And then during prompting, instead of prompting with original ImageNet category, I prompted with ImageNet sketch. Sometimes the model will generate me with sketch. Sometimes the model will generate me with real image. Not so off, but also it maybe understand a little bit that the sketch image and the real image are from the same similar category. Okay, now let's except for the most straightforward prompting, let's do a little bit more complicated prompting. Here we do some analogy prompting. This is the character from The Office. I also like it as well. So you can guess what should be next. It should be two skeletons, right? Cross skeletons.
So did the pre-training data have
Yes,
code?
yes. Yeah, so this is all in domain task, basically.
So this might not necessarily relate to this experimental setup in particular, but I wonder if you think that considering whatever multi-model models may be chosen, do you think it would be the case that cross-modality analogy detection would be more or less or similarly difficult to accomplish relative to analogous inputs coming from the same domain modality? So for example, creating a pun that's based on linguistic resemblance between two words versus likening an image of something to a concept that's represented graphically.
So multimodal here basically means if I have basically adding text in, would it be more difficult or more?
Yeah, so
Yes.
I'm maybe not fully certain about how precisely we're defining what analogy is in this context, but presumably it involves some and varying level of abstraction that is based on some non-obvious, non-superficial resemblance between two distinct things. And this is strictly visual, but I'm wondering if in the case of multimodal models, one could try to generate analogies that are across modalities. I don't know if that makes sense. I'm sorry.
Yeah, I mean, I have some examples that I find is kind of hard to describe with this text. We can see it later and discuss it later. But when it comes to the image-based prediction, I think even if, for example, you add some text in front of it, it would still not be that trivial because you need to generate instead of just some image understanding problem, still need to generate an image or generate a bunch of images. So it will still be hard. Right, yeah, so okay. Right. So we can discuss about this later. Right, so this is in-domain task. This is already seen before. You can just do it. This is a prompt result. You can do it on edge, depth, segment. This is surface normal, low light, highlight, colorization, and something more. And of course, because reviewer to ask, so we have some response. Right. Okay. Now let's see something. Things start to get a little bit more interesting now. As I mentioned that eventually what I hope from this model is not just the things that is trained before. It's more like after I show a little bit of everything data, can it start to do something that is a little bit more complicated? So in this case, I want the model to, instead of detecting with COBOL data, although I prompted with COBOL data, I want to see if we can detect me with this comic book cat. So this is comic book cat detection. So in order to understand this, you need to understand a little bit of style transfer and a little bit of detection. And here, this is a painting task. And this is just some black pixels. And this is the one without black pixels. And I prompt the model with this. This is actually invisible triangle. This is very fun. For example, because this is what the model generates. The human beings can see that there's a triangle, but usually models can't. In order to prevent the model from the possibility of directly copy paste from the training data, what do I do here is I first rotate that image, recolor the image, resize the image. Since our tokenizer is non-semantic, so it's not possible that I can directly copy paste.
Have you tried different deformations such that this will fail?
Hey, no, I actually tried even more, like a bunch, because I have a very critical advisor, as you probably know.
I mean, the
right.
deformation of the image itself, I mean, let's say if you know, do a nonlinear adjustment to the image. So the straight edge doesn't line up. So I wonder what can you, I mean, some point human will not see it, right?
I see. That I never tried. I can try it. It sounds fun. But yeah, here, you need to be honest. Here, I think if you don't give any clues to the image, it won't make sense that it can actually generate something like this symmetrically. So at least you should give it some hints that, the model should figure out the context. So we tested different scenarios, like sometimes masking the edge, sometimes masking out the circle, sometimes masking out the invisible part, because the surprise is really strong. So if you don't look at the context, you probably would just connect them. This is pretty fun. So by doing this, actually the autoregressive model now can contain a little bit of special reasoning. Okay, then here, this is actually something I really like. So I was asked for a question that how do you know initially you need to collect all 50 data sets to train such a big model? Initially, I didn't collect all 50 data sets. I have this mindset of being diverse, but initially what I do is just line on images with 10 data sets. But there was one point during prompting that I know that this can probably be working is because this case. So in this case, this is some data from instruct-pix to pix. Instruct-pix to pix is kind of contains some data like, every folder, it contains several pairs of images that is some transformation. For example, sometimes the sentence being like, make something red, sometimes make this mountain become snowy. Every folder, you have one transformation and it has several pairs. So that means by using the instruct-pix to pix data, every kind of transformation, you only see it literally once. It's not like other data set where you have like similar transformation, but different data. No, in this case, you only see it once. But actually, we can prompt it. That means at least a large model, its memorization ability is strong. That's when initially I know that this can probably be scaled up a bit, that you can keep pushing it for even more data set. Okay, but this is just because I got too many questions, so I pre-answered that. So this is here, in order to understand that, you need to know this is make something orange or red, but you're not sure which part of it to make red, and this is Berkeley Tower. So, sorry. This is what the model generates. And this is all the prompts images. It's actually longer. You can check it, the original prompt in the original table, but this is all synthetic data, but it transfers a little bit to the real photo. And this is oil painting key point detection. This oil painting images is I just during prompting and generated by myself, so it's never appeared in the training data. In order to understand this, the model needs to understand a little bit of what is style transfer and also a little bit of what is skeleton. So here you don't think then we started facing some scenario that you actually don't have this run truth because the complexity now grows up a little bit. And then this is cartoon image depth estimation. This is also out of domain data. Now the task is not out of domain yet. A little bit, a combination, I would say. But the data now is at least out of domain. Okay, previously we already showed, I want to push this forward. So previously we already showed that with some kind of synthetic observer's data, after giving it some prompts, you can rotate the model a little bit. This is not surprising.
Sorry, go back a little bit, the previous one.
Yes.
I just wondering if you reverse the order, depth map first and the RGB image, how the system not predict the next? Can we reverse the prompt? Can you just generate the image based on depth map, or that's not enough information?
I never tried. I should have tried. I should have asked you to give me suggestions. I never tried. But I think the model previously saying something like this here before. Right here, I actually for this I use some like C53, C52 stuff to randomize it. So I think this would have a chance. Now, yeah, we already seen that synthetic data can rotate a little bit. And then I use some PowerPoints during testing. This is now trained in the training set. I just add some, not wrong, but like square key points on some key points I picked into the training data just during prompt. I've never seen it during training time. And then I put some real images and give it some similar key points as well. And I want to see what would happen. This is some more example. So in order to understand this, you need to know that, this are some larger scale of analogy prompting. And within the analogy prompting, this is sequential prompting. And you have this unseen key point before. And you also need to keep the key point while rotating the model. This is start to be something that is a little bit more complicated than we trained before. And in this case, I really want to make the task even harder. So I just put different color of the key point and let it rotate. While I make the rotating degree very large. So previously it's almost like 15 degrees. This is at least 30 or something more. Try to let the model rotate the image. Okay, now it's the fun part. Some unseen task. Let's first see the last row. This is 1 apple, 2 apple. It's supposed to be apple. I also use PowerPoints to edit that. 3 apple, 4 apple, 5 apple, all the way down to 7. And in the end, the model generates me with 8. I don't think it's counting yet. I think it's just some replication or just longer. I think it's the model doesn't understand it as counting yet to this stage. It's more like just increasing the length a little bit, the more low level understand. And then here, this is 1 popsicle, 2, 3, 4, 1 fruit, 2 fruit, 3 fruit. And then in order to generate me 4, the model needs to squeeze a little bit and push it out a bit because it's too squeezy here, it can't fit. This is pretty fun. And then this is also some unseen task. This is light changing. The light is moving from the top to the bottom. I picked some animal that is with a bigger nose, so you can see it clearer that this thing is becoming darker and darker here. And then this is like make it larger, resizing. One thing that should be noticed that in instruct pix to pix or anything pix to pix data, this kind of editing the size of the object is a difficult thing to do because the model is only trained with images. But here it is not that difficult because during training, you actually seen a lot of videos, like egocentric videos or like this is camera pose changing videos. So for the model, actually, since you train it not just with images only, but also with videos, this task becomes a little bit easier for the model to do compared with previous image level pix data. I think it must have seen something like this. I don't think that is totally unseen before. I'm just saying that not specifically trained with this task, but I think it must contain a little bit of something like this. Okay, now this starts to answer your question. Because in this case, I feel really difficult trying to write, like when we're writing papers, I don't really know how to write the captions. So, and it strikes me, okay, then that is actually the motivation of why I'm doing this paper, because sometimes something in vision is just hard to describe in text. So now I'm just gonna play it. I'm not gonna say anything, just watch it and guess. I actually checked. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, 6. And this is also one line more. I don't think the model understand the concept of counting yet. I think the model understanding is like a zooming of the camera, like what it observed in the egocentric videos. But still something is happening here. This is the case of real life. So there will be some cat, a certain type of cat that, with the color would change based on the temperature. And this is a gradually darker cat. And this is called the model generates. This is actually a cat, because if you look closer, these are the eyes. This is not something that is cat shaped. This is actually a cat. Oh, this is in Chinese, it's called 逐渐黑化过程. Right. Instead, in order to understand that, I can see why the model can do this, right? Because I already showed it with what is category, and it understands a little bit of what is color changing during the time. So in order to perform this task, this naturally composed task, it sees a little bit of what is category, and it sees a little bit of what is color. I think it's still, as I said, not truly generalization, because I don't think, even for large language model, which language is more compact, more abstract data, that is true emergence would exist, but at least some kind of compositionality here. And also, since this is 3B model, this is basically the smallest version of a large language model. But it's interesting to see that it start to do something that is more complicated. Look at the eyes, so cute. Okay. Now it's IQ test, people. You need to guess. This is a test for you too. So I was told again by one of my very senior advisor that, back in 1960 or something earlier, you have that. What are the primitives? Sure manipulates. I want to say question, sorry. I can get to it later. Okay, so the Riemann's progressive test is basically a nonverbal IQ test. Basically meaning like, in this case, you need to guess. This is nonverbal being like, you can figure this out just by looking at the pixels. So in this case, what would happen? Okay, have a guess?
A.
Yay, A, right. Okay, since I mentioned that perplexity is used as a very common.
I think maybe the question is it input just pixels?
Oh, yeah, so
Mhm.
here. If you remember previously, we can do something like this.
Right.
So you can actually use this masking to enable this spatial reasoning. But because there's a reason why I don't just leave it blank. Because the VQ tokenizer, the backbone in a still CNN-based backbone, that means there would be a chance that the model can look at the global things to be able to leak. But in this case, I just mask it out in pixel-wise, so there's no chance the model would cheat. Right. And then again, to prevent it from just copy and pasting from the internet, which because I cannot really check every one of my images. So I resized it, recolored and randomized the recoloring, and also I just randomized also the masking a little bit too. As long as it can cover, make sure it can cover the bottom right. I did some randomization here to make sure that it's not the exact image. This is what the model generates. So it's not bad. Look, it can guess it's right. This one is very complicated, very complicated. It even takes me some time to think about it. But here, this is what a model generates. The problem is it looks kind of right, but I cannot fully make sure that it is right because, again, since the tokenizer's reconstruction is not perfect, I need to find a way to test if it's actually right or not. So also because of the help of the reviewer number 2, I also did some perplexity tests, like I choose 10 IQ tests. And then similarly, you can do perplexity, right? You just mask region and show the, and let the model just directly generate it and compare the generated images to the ground truth image, whichever choice that has a lowest complexity would be the answer. Well, it's not bad, and compared with the chance, it's still a little bit better, but it's not great. So I want to see what in this, like, I want to see if there's something more that I can understand. So as I ran around 900 experiments on this disentangle the synthetic task. So the task here, this is some images from the previous visual prompting paper that, by prompt the model with some, you can actually change the color prediction and change the shape prediction or change the size prediction to let the model generate. But basically, I think roughly, there like color, shape, or size can be some important factor in this IQ test problem. So for each one, we randomly generate 300 examples. It's 900 examples. And then with the same perplexity evaluation matrix, we let the model evaluate it. So it turns out the model is really sensitive to size and do relatively good on the color and the shape compared with chance. Okay, now let's see some failure case. Oh,
Sorry,
hi.
going back to the previous slide.
Yes.
What is the setup here? Are we choosing from one of three or one of two?
Yeah. So like for color and shape is 1 of 3. For size, things because the resolution of the image, the size doesn't look too different. So I just use whether small or large. So this is
and the setup here is just these K options and you evaluate complexity.
Yes.
But each one selects the lowest complexity.
Yeah. Right. Let's see some failure case. I really like this failure case because during prompting, we try really hard to prompt it. The first 2 examples I really like because it also shows something about vision, the difference between vision and language. Here, in this case, you have 1 apple, 2 apples, 3 apples, 1 pair, 2 pair. So I thought it would generate me with something like 3 pairs because this is some kind of analogy prompting. But instead of generating me with 3 pairs, it generated me with a apple colored paired shaped stuff. Why? Because the change is not like this is the interesting difference between vision and text in my method. Text is more semantic stuff, while vision contains a lot of dimensions. You have your lighting chain, you have your semantic chain, you have your angle chain, you have much more dimension. So when it comes to prompting, sometimes the model can get confused because it's just too many dimensions in the world. But it also says something about when it is the time that vision problem cannot be fully described by text. For example, if I take a picture of what we are right now and I label it, so this is a photo of a meeting room. That's it. It cannot see anything more. But what we can observe that human beings are movable. The tables sometimes are not movable. Each one of you is occluded by some other person, and this person is sitting a little bit further away. And when I grab a cup, I grab a cup like this. I don't grab a cup like that. And the cup is staying on top of the table. It doesn't stay behind the table. So these are all the things that won't be described in text. So this is what I'm saying, that if you want to use multimodal training, and if your prediction task is also very hard, then I think the model still would be hard to cheat, because in this case, only semantic description won't actually solve you the whole prediction problem, because vision problem just have many dimensionality. So I think we would have a chance of doing multimodal here. Okay, the second example here. Again, one of my advisors really like object removal, so he was making me do it. But I don't have that kind of data set of prompts, so I manually created by some online diffusion model. Every time, but the diffusion model isn't that great. It's kind of like when you're doing Photoshop to make yourself prettier. It just loses something. For example, every time I remove something, it leaves something blurry here. And then I remove the bookshelf. This is something blurry here. And then move something. So eventually what the model thinks is, I want to make the whole thing blurrier. Instead of just doing object removal, it's doing something that is blurrier and object removal at the same time. Again, so that is why I'm saying that this is interesting difference between vision and language. In computer vision problem, it's very noisy data, but also it contains much more information. That's why here in this paper, what we're interested in see is like if we only have like vision data, how far we can go. Right, and again, this is very small vision model, a very small model comparison LLM. So I don't believe in the true generalizational ability here, but still, I'm still a little pretty happy that at least it can start to do something that is a little bit more complicated. That's it. Thank you for listening. Do you have any questions?
Questions? Yeah.
Is there a way to start comparing the emergent capabilities of your model with existing vision language models?
Emergent problem. So,
You showed a number of cases where you did analogy prompting for various tasks, right?
yeah, so one thing, for example, like in GPT, at least in GPT or in the Jason Way's paper, the emergent properties of large language model, the definition of emergent property is like when something doesn't show, when we have like a small, like for example, math problem, it doesn't really work when you have a smaller model size, but somehow if you increase the model size to a certain level, then you observe a noticeable improvement on your matrix, right? So that means the original definition of emergent property is not like, this kind of unseen data generalization ability. It's more like when your model reaches to certain capacities, can it start to do something that is much better. But later people actually find out that because that happens because sometimes our evaluation set is just not diverse enough. For example, maybe you already start to do understand math a little bit better. 1 + 1 = 1.5 is also a bit closer to the 2, but since it's already also wrong, and maybe the coverage is not the whole math problem. So maybe the things you already learned something that is more, it just hasn't shown up in the evaluation matrix yet. So actually, people have tested if you have more diverse of the data set, maybe this curve can be. So, right, in case of this abrupt change, I would say that the main difficulty of vision problem in evaluation here is, as I just described, like the many tasks we have because of the real world complexity is actually disentangled task. Like we would assume that in COBOL data set, there would be no lighting change, there will be no occlusion, there will be no anything. It's just always this many of category, and it's all pretty beautiful images. So when it comes to this kind of emergent property, that means it hasn't trained, it needs to be real life. We don't really have that kind of data set to evaluate yet. I was hoping that maybe we can, like for example, some maybe more corrupted 3D rotation will keep point this kind of data set. But yeah, it's different from languages also, which is already human encoded and very abstract. It's just easier to evaluate there. So that is also one problem we really want to, like, how can we move from ImageNet data to actually more complicated real life problems, right? Then we need the whole thing set up. We need new benchmarks, new data, and new everything, new evaluation, new way of seeing this problem. Hey, hi.
Yeah, so I have a question about,
Yes.
prompt engineering with respect to this model. So in the example that you show, when you have 1 apple, 3 apple, 1 apple, 2 apple, 3 apple, and then you have 1 pair, 2 pair, about 1 pair.
Yes.
Say if you increase the length of your prompt, if you have like more examples with features, like, would that improve your result or no?
Yes, it would. Actually, I was asking about a question about how would the context length influence your result? And the thing is exactly as what you said. If you have a pretty simple task, for example, previously I showed if I have like this synthetic prompt, because it's like a synthetic created, right? It's not that contains that many of dimensions like simulated data. It's actually pretty clear to the model because this is also like a simulated. Or if it's an easier task, we tend to need less context to be able to figure that out. But yes, if it's that complicated problem with which contains non-semantic change, also lighting change, viewpoint change, then probably we need longer context. roughly evaluated on some case, but that's a very, very good point, yes. So then that also raises another problem. Compared with text, which is highly compact and highly semantic, vision itself is actually more redundant. And it's just longer because sometimes you can just sit here forever, right? For an hour doing nothing, like what I do in the lab for the first hour. I just sit there playing with my phone, doing nothing, no information increase at all. But somehow it's you in order to tackle with that, you need longer context. You need to find a way to compress the model or compress the data. It's not that is something that is intrinsically different. I think it's also very hard for me to solve in this case. That's a very good point.
I had a question about the tokenizer.
Yes.
So when you build a tokenizer,
Mhm.
like, would you consider the support of all the tasks that you are considering for the final evaluation, or how good should this tokenizer be considering this imbalance in terms of?
Yes, that's also a
task
very good question. In my mindset, what is tokenization doing here? Or how can I make sure that, this tokenization is good enough so I can move on to my experiment? The way I think of it is a compromise. It's a compression algorithm. For example, just like JPEG or what we're using right now, because in the extreme case, considering I'm not that poor as a postdoc here doing it, considering if I have instantly amount of compute, I can even do it on pixel wise. Like in the extreme case, well, IGPT is still representation learning with this is all regressive model of OpenAI several years ago. It's a crappy comparison, it's a crappy pixel because it resizes it too much. But still, if you consider if you have instantly amount of compute, at least starting from 16 by 16, I can do 32 by 32, 64 by 64. Even, like I said, even in the most insane scenario, I can even do pixel wise, so that I won't actually need to worry about this kind of reconstruction loss. In this case, that's why I'm saying that this is a compromise. So initially, we just trained it on line images, and I tested on some data set. As long as it can generate me good enough, reasonable, I just make do with it. I mean, I think every part of this paper can be improved by a lot. You can always use a much better tokenization algorithm, longer context, larger model, better data cleaning. I think this should all improve the result. And also you can use some stronger decoder because people actually observe that if you have used some like diffusion-based decoder or just simply increase the decoder size, you can get a much better reconstruction result as well. But here, I just viewed it as some make do thing that as long as I can make this whole thing running, as long as it's good enough, then I just view it as a little bit crappy of compression. Does that answer the question? Hey.
Cool. I love the work. I think the analogy to language models is really exciting. I guess I have a few questions in terms of the early motivation.
Mhm.
You seem to be motivated by this question of scaling data and the fact that MoCA fails at you just can't keep shoving data into it and see improvements. I guess in this case, and what you've done, you have a mixture of data, some of which is supervised, some of which is unsupervised. One thing that we found in the LLM literature is that different data matters a lot more. Actually, in the setting that you say for the internet dump versus Wikipedia, actually you have to run a lot more on Wikipedia. Wikipedia is small,
Yeah,
but it's the
oversample.
most
Yeah.
valuable data. If
Exactly.
you don't run on it, actually you get bad things. Right? More so than running on the whole internet. Actually, Wikipedia.
Yeah.
I wonder if could you maybe say a little bit about the relative value of the
Yes.
supervised data versus unsupervised data
Yes.
and how that affects your sense of whether this actually is scaling that data?
So I think I sensed three questions within that question. So the first question I want to say is like my motivation here. Is I wasn't really targeting at data only. I was targeting at the whole representation paradigm. What we do early is, we train on one single data set and we keep the representation. And then we leave out whatever the rest of the MLP and, or the head, and we add another head on top of it and just use the model as an initialization point and fully fine tune it on a totally different data set. But if you think about like how language models are doing, they do next token prediction for the pre-training, but they also do next token prediction or instruction tuning or post-training in the fine-tuning stage as well. It's not like they're using two different laws for the pre-training and for the fine-tuning, and then many things can just simply tune out, because what I find out for representational learning is as long as you have a very strong fine-tuning recipe, sometimes your pre-training doesn't matter that much. There would be a gap between this pre-training and fine-tuning thing. And also, the previous mindset would be we train on one data set and hope it can generalize to other data sets. So here the mindset would be what happens if it just doesn't generalize that much. That's why we want to add more data in. So we are not, and we actually have a huge Google sheet about every possible factors we evaluated. So we are targeting at the motivation, we're targeting as a whole paradigm instead of just one. It's not just training, and also not training on image data for 1600 epochs, but also new data, every time new data, just one time. To see if when new data comes in, do your training loss still decrease? Because one thing we actually observe for the original ME algorithm, not just downstream tasks, but since the training stage, the model is already saturated. I can show you some result. Can you see my screen?
No.
No. Right. I can share screen again. Right, can you see this? Oh, sorry. Hold on. Yeah, but this is what you get from having that much. Okay, so here, this is original MA setting, and this is training apples. We start from 800 image net apple and 1600, 3200 apples. Till this point, we don't have fine tuning yet. But if you look at the training loss, from the training process is already saturating. It's not even, we don't even talk about the fine tuning stage, this training stage. You just don't have lower loss with the training progress. What does it mean? We actually find out that after the model, for example, the random patch fulfilling this problem, when your model knows that, given this patch, you can fulfill by learning from some local cues instead of, you don't really have to learn something that is harder from that. So the model don't have enough motivation to keep learning. So this is the one point that we're not, when we're talking about the motivation, it's not about just one point. I think it's about the whole training paradigm. And also the second question would be about the data mixing problem. Yes, I think in GPT-3, like I mentioned, right, when it comes to a common crawl, which is 410 billion data, they actually use 60% of the mixing ratio. And for the web text tool, Wikipedia, which is a much smaller data set, which only contains like less than 10 B tokens, but they oversampled it. Basically, they do a data set mixing. I think that would improve the result, at least I think for the task-based, any task-based thing I've tested here, that would definitely improve the result, but unfortunately, we don't have enough computer.
Well, I actually think you do have it. So if you go back to the perplexity
yeah.
slide,
Yeah, okay.
where it was like images plus labels, videos plus images plus labels.
This one?
Yeah.
Oh, but this is not mixing with propulsion. This is just one apple, just directly whatever.
Yeah, but so
yes.
I guess maybe my question is, when I look at this graph, I see that most of the work is done by annotated data, right? Like if you look at the relative perplexity, right? Like, yeah, it's fine. You throw in unannotated data, things get a bit better. But almost everything you actually get is from, supplying real annotations.
Oh, like for example, here, like this is I think, sorry, because this is video only that contains no task and it's just.
Yeah, so that's like completely unsupervised.
Yeah.
But the rest, but
Yeah, like here,
those are
actually the
supervised, right?
perplexity is like six different, the perplexity difference is six, I just, because this bar is too high, I didn't draw it properly, so.
yeah, so my understanding is correctly that basically is that like orange, like gold bar is images plus labels.
Yes,
green bar is videos plus labels and images plus labels.
No, green bar means this part of data plus this part of
Oh,
data.
I see,
Yeah, it's more unsupervised data.
I see, I see. I see.
Yeah, also, this evaluation, like I just mentioned to him before, is not complete. For example, we won't test for the already existing benchmark, you won't test the out of distribution data, right? And you won't test more complicated tasks, just there's no way to test it properly. For example, if it's just semantic segmentation on COCO, it is just semantic segmentation on COCO. It's very fixed data distribution. So maybe there would be something more that can be tested, but due to the current evaluation algorithm, we cannot just. But yeah, this means more.
So I guess I'm with you that definitely unsupervised data is helping. Do you still feel like a lot of the work is with the supervised data? I mean, this seems like like a natural experiment.
Yeah.
Just if you're gonna run this twice,
Yeah.
run it.
Yeah, yeah.
Because the unsupervised data will actually scale.
Yeah, so like I said, there's a reason there's actually two reasons I think why I want to add this kind of supervised data in. The one reason is create the diversity. Like I mentioned, you just won't have for example, if I'm recording my daily life, the video I saw every day is like I would see like a different kind of PG student. Every one of them is a one frame, and I know there are some intrinsic connections between them. But the previous video data set I use is mostly like action recognition when it's not, it's just, you know, someone playing basketball or someone brushing the hair. It's very, very not that diverse of data. It's very constrained and very biased towards some human activity recognition data set. So that's the first reason why I'm creating some other kind of visual sentences in with some other kind of manually created diversity. The other thing would be, I would want something to get the knowledge out. For example, we all know that by being able to predict the next frame, the model must have already understand the concept of what is an object, right? Because since you can predict the next frame, right? You probably already understand that the human being is different from the background. You probably already know that. But how can you get that part of information out? You somehow need some kind of a tool. We actually did some experiment that is never shown in the paper, but I find it to be very interesting. Is here. This is again PowerPoint drawn mask. So the 5 of them is just 5 random seeds, and each line is like this is one image, and then I prompted with the object segmentation of the object that the hand is interacting with. For example, if the hand is operating on the tape, I prompted with the tape segmentation. If the object is holding the milk box, I draw like a milk box segmentation. And in the end, I prompt the model with this frame, the hand interacting with the green pattern. And I found out the model is actually not looking for the hand anymore as I trained, but start to find the object that the hand is interacting with. What does it mean? It means the segmentation that the model is doing here is not defined by category. It's defined by the context that I give it. It means like, can you give me the object segmentation that every time a hand is interacting with it? So this, for me now, what does this segmentation mean? It doesn't actually mean the original segmentation I wanted to be. It's more like a tool to get the information out. Because unlike the text, we can just say it, right? We can just say what do we want. But in vision problem, many of the time, I can't really get it out. I know the model must have learned something. So there's another reason why I'm adding this kind of data in. I want some hook.
Okay, so the other part of
Yes.
language model pre-training is supervised fine-tuning, which like
Yes, that.
no one's actually ever interacted. And imagine no one in this room has interacted with a language model which is not that supervised fine-tuning, because it's impossible to touch. Like you can't prompt anything to go out there.
So what do you mean?
Like most language models actually do this kind of
Yeah.
other supervised fine-tuning.
Yeah,
I mean,
we
I'm
have
wondering
a
if
very
maybe
happy-
what you've done is actually just mix the two phases,
Um,
right? Because there's
I
the
think-
fully
yes.
unsupervised and then actually.
Because I think that also there's one difference I can mention here. For languages, every sentence already means something. For us, I want to create a possibility that you can do a more real life complicated task. Like, can you detect me something that is under low light environment and it's also raining and the person is also moving? I also want some kind of task done during pre-training, like this kind of, if you get my point, it's not.
There's a lot of implicit tasks that are learned in language models. For example, when you do syntax. for free.
Syntax.
Like you could go talk to linguistics department, get a syntax course, and then actually extract those things from language models.
Yes.
That aren't trained for these things that happen implicitly.
Yes, then probably I think if we're gonna achieve that, I would probably need more diverse of internet video and then move this to second series. I think that would be possible too, but like by the time we don't have that many data set, but I think, yeah, in the end, in my mental model, like I mentioned, I think only video would work in this case, as long as it's diverse enough. I think, yes, we can actually move that into the fine-tune series we have, right? I think, yes.
Okay, I was just like wondering in the follow-up, because I do happen to have quite a bit of background in formal semantics from the linguistics side of things. So it's quite unfortunate that the interpretation of the word semantic means something very different in the current paradigm of large language models. And so in linguistics, the way you deal with the semantics is via the syntax semantics interface, right? Because linearization only matters for phonetics, but language representations in all the other domains within linguistics, be it morphology or syntax, are inherently hierarchical in a very like nested tree kind of structures, like those are the grammars and whatnot. And the semantic computation is done such that at the interface, you get those entire hierarchical tree structures, you get the corresponding lexical entries, which are the most reminiscent of how we typically conceive of what semantic embeddings are in the context of this kind. And then like using tools from lambda calculus and whatnot, which is like applying the compositional rules until you compute a final. And so this is perhaps a very broad question, but I'm curious because I know that even though the state-of-the-art large language models do not really have any sort of explicit mechanisms for encoding syntax in the formal sense, it has been found repeatedly that sometimes as you move towards like later layers and whatnot, they do seem to be picking up on certain syntactic patterns, but that's almost as a side effect of the training data that contains syntactically well-formed structures. And so I'm curious how you think the architectures of current large language models could be altered to enable rules for composing sentences that is aligned with the framework of, I guess, like generative grammar.
Wow, that's a very long question. I probably need a like larger brain capacity to handle that. Right, is that going to about how to design a better large language model structure?
More like maybe so. The reason I'm asking was that it was quite interesting when you mentioned that relative to text models, in the case of vision and images,
Yes.
the data we are dealing with is inherently higher dimensional and also more noisy. And I'm curious if that necessarily needs to be the case. And also like, if you're familiar with any attempts to enforce structures of syntactic well-formedness that goes beyond simple attention architectures.
Sorry, this is all to all of distribution for me already, but right now I can check it out. Sorry.
I'm sorry.
That area of knowledge. Right. But I think at least in our case, there is already some simplification of this, like we have tokenized it. I think it already somehow get rid of the noise a little bit. It's already compressed a little bit. And also we have some spring selection. It's not like we train is everything. I actually wanted to be trained on things that is actually changing. So there is already some simplification here. Right. Sorry, I don't really understand your question.
It's more like I probably just like don't understand this enough to give a normal question, I'm sorry.
Okay. All right, I think it's, so we're running quite a bit late, so let's thank, Yutong again for a great night.